In this video, we'll describe a trick that's very useful and very general for improving any object recognition trainable system like a convolutional neural network, which we will refer to as dataset expansion. So we've seen that in a convolutional neural network, we get some invariances that are essentially built in. It's invariant to small translations thanks to the convolution and the max pooling with subsampling. It's also invariant to small elimination changes if we introduce some contrast normalization. However, it's not built in as to be invariant with respect to other things like rotations or changes in scale. And you'd imagine for, say, an object recognition application, because the object doesn't necessarily change if we zoom in or zoom out in the image, or if we rotate it a little bit, we would like to build in or to encourage that type of invariance in our convolutional neural network. There's actually, but it turns out that these variations are actually very easy to generate artificially. It's very easy to just take an image and rotate it somewhat or change the scale at which we're looking at this given image. So a very easy trick for improving the performance of a computer vision system is to actually generate this artificial data and put it into our training set. So expand the training set using these transformation to guide us into how we could generate additional examples. And so by doing this, by generating this additional training data, the neural network will instead learn to be invariant to these transformations because they're explicitly there in the training set. It will get explicitly the signal that it should perform or output the same object for any variation in the rotation or scaling that we'll generate. So here's a cartoon illustration of how we could generate these additional examples. So now in each case, we'll essentially take a smaller portion of the image and we'll apply a transformation to it to get, and undoing the transformation to get an image in the same reference frame. So for the original image, we just take some crop at the center and that would become a new training example. Then if we want to be invariant to translation, we could take the crop of the original image and instead translate it somewhat. And then we would take that subset of the image and this would become our new image. We could, if we want to be invariant with respect to rotations, we could take the crop, the original crop window and just rotate it randomly. And then we would consider only the pixels in that window and we would undo the rotation to get again a rectangular image like the original image. And similarly for scaling, we could just take the cropping window and instead change its size. So if we made it smaller, then we could crop fewer pixels and then we could undo this cropping by scaling back to the same size as the original image here, in which case we'd get a zooming operation. So we'd be changing the scale of the actual image. So for performing these operations, I won't go into the detail. You need to do some sort of interpolation of pixels when you're doing these real-valued rotations or scaling. But often, if you have some software that allows you to manipulate images, you can do many of these operations. They often support it. Another type of additional examples we can generate to improve the generalization performance of a computer vision system is to add so-called elastic deformations of the image. This is particularly useful for character recognition. So the idea is that we want to take some original image and sort of locally distort it a little bit such that it still looks like the same kind of object, but it's somewhat a little bit different. It has a slightly different appearance, but that still qualifies as an appearance for that same object. So one way of doing this is to first generate a random distortion field. So the distortion field, which we see here, would be for each pixel a vector that tells us how the value of that pixel should be displaced into dimensions. And so if we generate a random distortion field like this, well, you get a bunch of arrows pointing in random directions. So they're generated here each using some Gaussian, where each sample, so each vector is generated independently. So we're generating each point, which is a vector, as a two-dimensional from a two-dimensional Gaussian. And now if we apply that distortion field to the image here, for instance, we'd get something that's actually a bit noisy. It's not a very convincing 6, and it just looks like we've just added some noise. However, if we take that random field and we actually smooth it using some smoothing kernel and doing a correlation or convolution, such as, say, a Gaussian kernel, for instance, then we can just smooth this original random distortion field to get a smoother transformation. And if we apply this distortion field that's been smoothed, then we actually get something like here. This 6 has been transformed into this sort of deformation, which still qualifies as a 6. It's a pretty convincing image of a 6. And so by generating many of these distortions, so we get another one where we generated a random distortion and then smooth the distortion, we get a new 6 here, which is actually quite different from the previous one. And it's still a very convincing 6. So we see that this is another kind of operation which allows us to generate for free additional training data. So we would just add this as in our training set and label it as 6. Again, you need to be careful with in order to do some interpolation of the pixels, because this is again a transformation which is continuous. So it's not, each vector does not displace the pixel necessarily exactly on the original grid, and so you have to do some spatial interpolation. But again, this is the kind of thing that's often supported in softwares that allow you to manipulate images. To get more details about all of this, I encourage you to look at this Simard et al. Paper that is referenced on the website for this course. And just remember that these elastic deformations or any of the other kind of transformations we can use to expand the data set is not actually just useful for neural networks, but really any system that is trainable. All right, so that's it for data set expansion.